Guys, can you hear me? Hello? Okay, nice. So we will wait a bit to see if someone else attached to this live, and then I will start with the presentation. Let's see, you are 7 people. Let's wait like 5 minutes or so. Let's see. Let me prepare the other stuff. Five. Okay. Okay, also Giorgio reach us. So you guard the chat, Giorgio, and also tell me if I have to start, but they are really just 5 guys. Okay. Hi to the student that is at the cinema in Diag, newly open. Let me open this thing. Okay. So guys, today we will speak about localization with Kalman filters. Kalman filter specifically is an example that we write in Octave for you to try. The lecture will be scheduled as follow. Like I will introduce to you the exercise, like the different parts, the domains, and blah. Then we will open a Google Meet with Giorgio, and we will do the exercise with you if you want to. Anyway, I will publish the solution of the exercise on the Git repo, so that you can see it anyway. So let's begin. So that's the outline of the exercise. I will introduce to you first the scenario, so the type of robot, the type of sensor, and so on. Then we will speak about how to structure a Kalman filter in general. So we have to define the quantity that we want to estimate, the controls, the observations. And in the case of the Kalman filter, we also have to compute Jacobians. Then I will show you a bit how the dataset is structured, and then we will move to the Google Meet so that I can show you the actual code. You should find the code already in the repo. So the scenario, we have our robot, Orazio, which is a differential drive platform. So unicycle model, basically. And we can control it by translational velocity and rotational velocities, so in V and omega. You should have seen that in autonomous and mobile robotics, I guess, at this point, more or less. And is equipped with a really strange sensor, because it's a sensor which is capable of perceiving 2D landmarks, and also it can distinguish them uniquely. So it means that if you see the same point from different position, it can recognize that it's actually that specific point and not a 2D point in general. The location of those landmarks, so the environment is a 2D grid, and then we have the 2D location of these different landmarks, and this location, so the location of those points, is known at any point in time. Okay. So how do we approach the problem? There are two aspects. The first one is to define the domains, so the dimensionality of our problem. And I will tell you guys that that's it seems the easiest point of Kalman filter, but it's actually the reason why me and Giorgio, let's say, put lower grades in the exams generally, because the dimensionality is really, really important. So try to really focus on that when you approach any type of problem related to this specific thing, so Kalman filters, but generally to any problem in robotics. So we want to localize the robot, so to track the position of Orazio over time. So a robot pose in 2D is represented by an element of the special Euclidean group 2, whatever, so it's a transformation matrix. And then we have the controls. The controls are Euclidean because we have translational velocity and rotational velocity, V and omega, so it will be real space, R2. And as a prior knowledge, we have the map, which is constituted by 2D points. So again, that's R2, really, really easy. That's our prior knowledge. So this is the structure that you see here is what you will see also in the code. So each of these points have attached an integer, which identify this specific point from, I don't know, this other point, whatever. So these are the domains, as I explained to you before. So the state, the quantity that we want to estimate, is a transformation matrix, so rotation and translation. Then we have our controls that for the unicycle is translational velocity and rotational velocity. To make things easier, we pre-integrate this quantity. We will perform a Euler integration of the unicycle model. So we already multiply it by a delta t, so an integration interval. And so you have ut1, ut2. Remind that this 2 is not at the power of 2, is just an index. Okay. And then we have the space of the observation. So the map is made by 2D points. We can perceive 2D points, so the measurement belongs to R2 in this case. Okay. Now SE2 is not a Euclidean space because it's a transformation matrix, but we can find a Euclidean parameterization which is meaningful. And in this case, we have x, y, theta. So it's actually a vector in R3, even if theta is not really an element of a Euclidean space. This simplifies the problem and allows us to compute Jacobian easily instead of computing a Jacobian on this space. So that's a usual thing that we do with Kalman filters. We first model the state as it is, and the same is true for the measurements or for the control, and then we try to find a Euclidean parameterization for which the things get easier and we don't have to handle manifolds. Now the transition function. So we have defined the state, defined the controls, and defined the measurements. Now we miss the two building blocks, these two guys. So the transition model that given the previous state and given the actual control, but here is reported t-1 because in theory is the previous control, give us the predicted next value of the state, so the next configuration. And then we have to define also, we will see it in the next slide, the observation model. So given the current state, what is my prediction about what I should see in theory? So as I tell you before, our transition function is just the integration, is just the Euler integration of the unicycle model. So we have the previous configuration, x, y, theta. Then we have, this is a v in the AMR language to make easier for you to understand. Cosine theta minus 1, sine theta minus 1. This is the angular velocity, so for the Euler integration we are just going to add it as it is, as the angle was a Euclidean quantity even if it's not. Okay. Then the measurement function. That's the second important point when you face a robotics problem. Understand the frame where the quantities are expressed, and that is fundamental. I think you already see it in robotics 1, and that's another point where a lot of students struggles in general in our exam. So please focus on that really much. So follow my reasoning. We observe a landmark, but the sensor is placed at the center of the robot in this case. So actually our observation is in the robot frame, while the map is referred to a word frame. So there will be a point in the map which is the origin of the map itself, and then all the points are expressed in this frame. Now the quantity that we want to estimate is actually the relative transformation of the robot in the frame of the word. So in the Luca language will be like T of R, and then you have this thing there, W, okay? Something like. So given a landmark in a word frame, I have to make a prediction about what I will observe in the robot frame, right? And the transformation that I have is robot in the word. So actually I need the inverse transformation. So I need the transformation from word to robot. Then I will take the landmark in the frame of the word, bring it in the frame of the robot, and this defines my prediction. Then everything else came in a straightforward manner. So that's how you apply an inverse transformation. So take the landmark in the word frame, subtracting the translation, and then multiply it by the rotation. You can observe the same if you take the whole transformation inverted and then apply it, you will get exactly this formula. Is that clear? Someone? Clear what I say until now? I have a little bit of delay, so you will see 30 seconds of silence, I guess. Thank you, Martina. So, next. So we define the models. Now, what happened that our robot in fact doesn't sense a single landmark in each point in time, but actually is inside the map, so there will be location where we observe multiple landmarks in the same time instant, a subset of the whole map, of course, because the range of the sensor is limited. So what we will do, if we have multiple observation about the landmark, we just stack this observation in a gigantic vector. So our prediction will be a prediction related to a certain subset of those landmarks. And k is the number of landmarks that we observe in each point in time. Okay, it might be different from different timestamps. So another aspect, so domains, transition function, observation function. Now we need the noise models, let's say. So we have the noise in the controls and we have noise in the measurements. Both of those noise are Gaussian distributed because otherwise our Gaussian assumption will be broken, the Gaussian assumption on the state, I mean. So we assume that the velocity are affected by Gaussian noise, but we can take advantage of that actually to include in our model other aspects. So angular velocity and translational velocity in practice are transmitted through electricity, and this electricity might be affected by a small noise which is roughly Gaussian. Other aspect that regards a physical robot is the fact that, for instance, the two wheels might not be equal. That can be a problem, or the surface is not completely flat. So it means that if I tell the robot to go 1 meter forward, if there are hills, it will not go exactly 1 meter, it will go something less. So inside the control noise model, we can actually add this sort of effect by adding a term which is dependent from the velocity value. So we will have a constant noise on the controls, plus we will have something which moves like the square of the velocity. Meaning that if I go faster, I assume that all these other effects will bring me not in the position that I expect. So I model that, and that's a really simple model. Other exist, of course, but just for the sake of this exercise, we will have this constant term that you can imagine is related to the motor itself, and then this other term here, which instead is related to all these other effects that that we have in a physical platform. Okay. Measurement noise related to the sensor, we can assume it like a constant standard deviation, let's say, so a constant variance with a value sigma z. So nothing spectacular here. If you know your sensor, sometimes in the datasheet of the sensor they report this value more or less, or you have to compute it using some formula, but you can get this number pretty easily. While this is a design choice, depending on your system, depending on the quality of your controls, etc., etc., etc. So this is more a design choice. This is almost all the time given. If not, you can even choose it if you want to model special effects, but in general it's constant. So Jacobians. So is the, of course, I don't have to teach you how to derive a thing. The thing that I want to stress is always the dimensionality. So let's take this example. Our state is 3-dimensional and our controls are 2-dimensional. Now we are speaking about the prediction step of an EKF, right? So the A matrix, which is the derivative of the transition with respect to the state, will have dimension 3 because the output of the function is 3-dimensional, and number of columns equal 3 because I'm deriving over the state which is 3-dimensional. So it's, in general, when you derive a function with respect to something, the dimensionality is the dimension of the output of the function times the dimension of the thing for which you are deriving, basically, okay? So the A matrix will be 3 by 3 and the B matrix will be 3 by 2. Easy peasy. Why? Because the controls is 2-dimensional. So I will have 3 rows and 2 columns. Okay? I know that it seems like really stupid for me to tell you like that, but trust me, it's important that you remind that in any problem that you face. Understanding the dimensionality of the Jacobians is what it saves you in any problem in robotics, even if you're doing direct kinematics, invert kinematics, whatever. Okay, so 3 by 3, 3 by 2. Now we have the Jacobian for the correction step. So now I want you to write on the chat. So our prediction give us a 2D point. So what will be the dimensionality of this Jacobian? So the C Jacobian. Can anyone guess? I'm deriving with respect to this data. I'm looking at the chat at the same time. Hope someone try. Otherwise, Giorgio will try to guess. Two by 3, yes. Yonut, I hope I can read correctly your name. Yes. Yes, 2 by 3. So, point, dimension of this guy, so it's 3, right? The computation, I hope for you it's really easy, but I will rehearse it with you. So we have this guy derived with respect to the translation. So this guy became minus the identity. So we have minus the rotation transpose. This other guy is divided by the angle. So we have the derivative of the rotation matrix with respect to the angle, which is this guy. You can repeat the calculation, it's pretty easy. And here you get this thing, which is a 2 by 2 matrix for a 2 by 1 vector, so it's a 2 by 1 vector. Okay? So far so good. And that's the Jacobian for a single observation, so for a single prediction, better say. Then we have to basically stack all the Jacobian in the same way that we stack all our predictions. So nothing spectacular. Okay. Now hands-on, just to tell you how the dataset is composed. So it's in G2O format. It's really easy. It's written like line by line is written stuff that you need. So you have the landmark data structure. This is an array struct in Octave, which means just a vector where each entry is something. You don't know exactly what, but it is something. And the structure is the ID of the landmark, so the unique identifier of that specific point in the world, and its XY position. For the pose, you have even here an ID, because of course it's a sequence of poses. So this ID of course will be incremental. First position is 1, second is second, etc., etc. Then you have this XY theta parameterization that we choose for the robot pose. Transition is always a struct, and it tells you the ID where the transition starts, the ID where the transition ends, and the velocity. Here you see just the V, but of course there will be delta t, delta theta, because we already integrate them. And finally the observation just tell you from which pose you see the thing and what did you see. Here inside of course you find the ID that refer to the proper landmark. Okay, and that's the filter where we are going to joke in the Google Meet. Just to explain you really quickly, you initialize the pose of the robot randomly, so you actually have no clue where did you start precisely. You initialize the covariance of the state, and then for each of the transition you perform in sequence a prediction step and a correction step, and then you plot the result so that you can see how the filter evolve. Actually, if you take this same structure and you change the dimension here, you can apply this code basically to any EKF that you will see in your life, because it's always this thing. So to recap, to solve an EKF problem you have to define the domains, so state, controls, measurement, define the transition function and the observation function, and at least you don't have necessarily to compute Jacobians, because you can compute it numerically. There are different tools that you can use, but at least you have to know the dimensionality of the problem, so the dimensionality of the Jacobians in this case. Then the rest of the filter is just an algorithm where you plug these things and run it, basically. So what we will do in the Google Meet is to fill the EKF prediction, including the motion model of the unicycle, and the EKF correction. So we will open the Meet. As I tell you before, I will publish the solution anyway, but if you want to kind of do it step by step with our supervision, we are happy if you want to join the Meet. Giorgio, can you publish the link of the Meet on the chat so that the guys can go, and then I will close the live in 5 minutes, more or less. There is any question? Sorry guys. There is any question about what I say? Something which was not really clear, something that you want me to repeat, and so on? Ah, you mean on the calendar, but then I have to switch stuff. and I don't know how to send it because my chat is on the phone, because I don't have multiple screen. So if you open the event on the calendar, okay, so Giorgio will send you the link via mail. I don't think there are any questions because I don't see anything on the chat. So guys, see you in the meet for those of you who will came, and see you next week anyway. Bye. Delay.